finish up that last lesson, 30th. Okay, we're up to the gradient, 8.1, and example B. Right, so in your notes I've provided you the space. So on the bottom of page, the second graph, on page 62, put a dash on Y. We'll look at that notation when we get to it. Looks like we're going to have something involving macros today.
What?
Right, so the first lesson on Mondays, now a few days old now, we looked at the derivative function, gradient function, sorry. So, we need to, there's the original curve, we need to sketch the gradient function. Okay. Could we just switch on the last set of lights, please? Just for the... Put it in front of the mirror.
Oh,
What
yeah,
does that say?
Just take that.
Just eat it all in one.
Alright, so let's sketch the gradient function, everybody. So we start with where the tangents, the gradient of the tangents are equal to 0. At what points are the gradients equal to 0 of the tangent? Okay, at the, what do we call them? Okay. TP. Two words, starts with T, second word starts with P. What's happening at the points? They are turning, so they're called
Turning points.
turning points. There we go.
That's physics. I just realised.
Alright, so there's the three tangent at the point. Well, I didn't literally draw the tangent, but we're just getting the representation of what's happening. Alright, where the tangent, the gradient, of the tangents are equal to 0. So let's dot that down. It's already on the axis. And dot this one down. Alright, so there's where the tangents are equal to 0, those 3 points on your graph. Alright, and from that we need to find either the positives or the negatives, and then do the other ones. Okay, so which point is the gradient of the tangents going to be positive? Let's label some letters now. A, B, and C. Okay, so in other words, to the left-hand side of A. Alright, if I draw any tangent to any point in the curve to the left of A, they're always going to be positive. Okay, different values of being different values, but they're always going to be positive. Where else?
C to B.
Between B and C, we draw tangent to any point on that is always going to be positive. Right, so I can think of it as, let's do the negatives first, So between what points, or from what point, are the tangents going to be negative?
A to B and to the right C.
Good. Okay. So you get an idea of where things are 0, where the gradients are 0, where the gradients are greater than 0, and where the gradients are less than 0 in your tangent. Right, so from that we sketch. So we are graphing the x value of the coordinate against the value of the gradient. Okay, and that's what we started looking at this topic when we looked at the parabola, and we're doing the same sort of thing. Alright, so to the left of A, the gradient is positive. Between A and B, the gradient is negative. Alright. So we've got a positive gradient. So underneath A, we've got a negative gradient. Between A and B, the value is a negative y dash. Alright, to get back to a B where it's 0, between B and C, we are positive. That means we've got some turning point happening between those two, but each value of your tangent is positive in that section. Then to the right of C, the value is going to be always negative. That will extend down in that general direction there. Okay, you are sketching the gradient function. So, these sketches don't have to be accurate. However, you need to provide to me the general shape and, of course, the correct location where they cross the axis. Any questions on that? Everyone got the idea what's going on? Yeah? Okay, that's now exercise 8.1. Alright, so I need to move on today because the extension students need the next couple of concepts. So, 8.2, differentiability. Right, so a function is called a differentiable function if the gradient of the tangent can be found. Okay, so we'll look at what we've done so far this lesson. The gradient of the function can be found at any point if we are given coordinates and we are able to calculate the gradient. Okay. There are some graphs that are not differentiable in certain places. So a bit of terminology to come up. Most functions are continuous, which means they have a smooth, unbroken line or curve. So this will be a continuous, it is smooth and it's unbroken. Alright? So from that we can differentiate it at any point. However, some have a gap or what's called a discontinuity. Alright, so in the graph of a hyperbola, so I was hoping to have functions and graphs done, but we've had a bit of a rearrangement in the order. So does everyone remember what a hyperbola looks like? Anyone remember what a hyperbola looks like? Yeah, good. I like that one. That's much better. Do it again, Kyle. Like that. I like it. I've never seen it like that before. But that's an example of a hyperbola. Okay? So in the form y equals a over x, so there's a certain value of x that it cannot have, therefore the graph is broken in a point, alright, and that will be an example where it's not continuous, alright, or discontinuous. So, this can be shown by an asymptote or what you could see it as a hole in the graph. Alright, and we'll talk about more about asymptotes when we do functions and graphs next topic. So the function is not differentiable at any point of discontinuity. Discontinuity.
Just continue. You got it. Yeah.
There's one bit, some words going to be hard to roll off the tongue. Okay, on page 63. Let's have a look. So, on that first graph, so the function is not differentiable at A, so we've got an example of a hyperbola, not at the origin, okay, we're shifted over, and we'll talk about that more in functions and graph, since the curve is discontinuous at this point. Right, the second one, the function is not differentiable at B, since the curve is discontinuous at this point. This goes back now to your inequalities work. Remember when we were graphing inequalities and we were just strictly greater than or strictly less than, we had the open circle. Alright? And that's this concept here. There is a break, something's happening in that part of the graph, okay, that's causing the open circle to be there. Alright, so we will say that function is not continuous or discontinuous at that point. Right? Now the last one on that page, the function may be continuous but not smooth. Alright? So we've got a continuing graph happening, but all of a sudden we've got a major change happening. So if we're looking at the graph at C, right, so the curve will not be differentiable at point C because we don't have a smooth transition happening. We've got a quick sharp change happening. So, a function y equals f of x is differentiable at the point x equals a if the derivative exists at that point. So we need to have a smooth curve and we need to have a continuous curve. This can only happen if the function is continuous and smooth at x equals a. I've got ahead of myself there. So, exercise 8.2. I've not got any examples on that because you're really just looking at the graph and deciding whether we have smoothness and continuous for all points on the graph. But what I really want to get into today is differentiation from first principles. Now, people hate this. I'm hopeful you won't. Alright, differentiation from first principles. So, we've talked about differentiation so far. Okay, differentiation is the process of finding the equation of the tangent. Okay, and that's what we're getting into today. So, the tangent is a straight line. It'll always be a straight line. Okay, when we have, since the tangent is a straight line, we can consider the value of the gradient as a secant. So remember the secant crosses at 2 point. Okay, becomes a tangent. So I've provided the diagram for you on your notes. So we have some continuous curve, follows that pattern there. Got 2 points P, and so let me just make it more sharper here. So we have the point P with coordinate f, comma some function of x, and we started talking about functions and we haven't continued it. Alright, so in other words, this is your x value, and this is the f of x axis. Alright, so it's a new notation that we started looking at before we realised that we had to do trig. Alright, now from that, let P f comma f of x be a point on the curve, and let a second point Q exist such that it's an additional unit, additional h unit along the x-axis from x. Okay.
You said it wasn't going to be there.
What?
I said I don't like the look of this.
Okay, so if we have x plus h as the value of q as the x coordinate, right? Any ideas? Well, probably on the diagram already. Yep. It's in your diagram. Alright. Right. So we have some function of we have plus h to get from point P to point Q. That means the point's already as f of x on the function. That'll become an f of x plus h on your function. Okay, as the value of q for the y value. Right, so we need to put the straight line between them. Not very straight, but you get the idea. We need to calculate the gradient of that line. Okay, so what's our gradient formula? Rise over 1. How do we write it algebraically? The order is important. Right, Nicola?
What?
She likes to use the gradient.
Yeah. Why's your board and name on the board anyway?
Something I need to talk to these two about, but Robin's away. Anyway. Right. Right, so let's call this one, sorry, y2, y2, x2, x1, y1, sorry.
Is the line going to be H?
The y going to be h.
No, the line. The line H.
Line's not going to be h, no.
Then where does the plus H come from?
Because I want to, we select a point Q that is h unit away from point P.
But it wouldn't be
But this is x,
vertically or horizontally.
this is x plus h.
Okay, yeah.
So you go h units that way. Yep, right. And then that means you have f of x here, and then you want to go from the change here, you're then going to have the f of x plus h as part of that. Right. Alright, so we have f of x plus h as y2, so we're substituting into our gradient formula. We need the gradient of the interval PQ. Take away y1, which is f of x. Okay, we get that from substitution over x2, so the q value, so it'll be x plus h. Take away y1. Which is, x1, which is x. Okay, so that's the substitution of the gradient formula for those points. Alright, we can tidy that up a bit further. Yeah?
Your YouTube thing.
Is it relevant right now? Is it?
What?
Is it relevant right now?
Oh, it's like h does not equal 0 since h is the denominator of the fraction, but we can take a limit. Is that the same thing as the pun?
Hey, what, huh? What?
No?
What?
Oh, you said your YouTube name had a meaning, and it's just here. It says, but we can take a limit.
Okay, we're getting there, yes. We are getting there, yes. Alright, fair enough. Alright, let's tidy this up first before I get to that, Kyle. Alright, so on the denominator, x plus h, take away x. So that simplifies to h. So, the idea is that I've got a secant here. Alright, I've got a line that cuts at two places. I want to create that secant into a tangent that only cuts at one spot. So what's the value of h have to be in order to change that secant to a tangent? At the point P. You want to change the secant to a tangent at the point P, the value of h has to be? Okay.
Will it just be fx?
Look at h.
H?
So if I want to change this secant to a tangent, okay, so a secant cuts at two places, the tangent cuts at one, or touches at one place, alright? What is this value have to be for me to achieve that? No? It's an obvious question.
Not. To make what? To make it wouldn't have to be less. Is it half?
Half, so I'm only getting halfway
Oh.
to there.
So 1.
No.
less than
Zero.
Yes. If I make h 0, that means I'll bring this point around to the point P, won't I? And I'll have a tangent. So one of those obvious questions. Nope. Okay.
it started again.
That's always happening.
So, as the value of h gets smaller and smaller, so if I pick a very small value to separate those 2 points, I'll still have a secant. Okay, so if I make it very, very small, let's say 1 over 100 value for h, alright, that means moving the point 0.01 across, alright, I'm still going to get a secant, but I'm very close to a tangent. If I do 1 over 1,000, 0.001, alright, so I'll get that point closer and closer, get the point Q closer and closer to P, but still technically have a secant. Yeah? So, if h is 0, that means the point Q is the same point P, and I'll achieve the tangent. But what's the problem? H is the denominator of the fraction, isn't it? I can't put 0 there because I won't have a defined statement. So, one of the other things I wanted to do with functions and graphs was talk about limits. So, h cannot be 0 because h is the denominator of the fraction. But we can take what's called a limit. So I guess I'm introducing limits to you today. So, as h approaches, I've told you smaller and smaller value, you have 1 over 10,000, 1 over 100,000, get very, very close. Alright, get smaller and smaller, we get closer and closer to the tangent. So to achieve that, we take a limit. So as h approaches 0, the gradient of the tangent becomes, we take the limit, with that notation, that answers your question now.
Yeah. This one has h instead of x.
So, thank you. Take the limit as h. Take the limit as h approaches 0 of the function of x plus h. Take away the function of x all over h. And again, I wanted to do functions and graphs first, and I had that first, but I decided to go away. But I need to teach calculus first because Mikhail and Robin need it for the extension concepts. Right, so at the front, f dash of x is the limit. So the equation for the gradient of the tangent as the x-coordinate of a given point by first principle is given by, there's your formula in the box. So we have I've already talked about functions of x, okay, so that's talking about your function where it satisfies the vertical line test, we've talked about already. Therefore, f dash of x, so this is the function notation, and then the dash is what's called the first derivative. Okay, which is what we did at the start of the lesson when we graphed the gradient function. That is the first derivative. Okay. So as well as f dash of x, we also have similar notation, y dash, which is how we labelled it on our axis. They're the two most common ones. The third most common one of the other common one, dy dx, and we'll talk about that more in the HSC course. And you also have the notation d dx of y, and we'll talk about it more later. Okay, that's the formula. We just derived the formula. Now let's look at applications of it. So, differentiate the following from first principles to find the derivative function. So, A, f of x is equal to x squared. So, we are finding the equation of the tangent. So, we are finding the equation of the gradient of the tangent at any point x on my parabola x squared there. So, in the formula, we need f of x, which we have. Okay, we need now f of x plus h. That's the next thing we need to write. Alright, so if f of x is x squared, then f of x plus h, every time there's an x in the function, I've got to replace it with x plus h. So in other words, if f of 2 is going to be 2 squared. Alright, f of 10 is going to be 10 squared. Okay, that concept's what we're working on. So the f of x plus h is going to be x plus h all squared. Alright, so we need to expand that. X squared plus 2xh. And of course, all masters of expanding a quadratic like that. Alright, so the first derivative, f dash of x, we take the limit as h approaches 0. Of f of x plus h, take away f of x, all over h. Right, so we haven't taken the limit yet, so we need to keep writing that section of it until we do the work with the limit. So, f of x plus h, we replace it what we've just expanded here. So x squared plus 2xh plus h squared. What do I write for f of x? X squared. All over h. Bless you. Alright, you now need to tidy up the numerator. So I've got x squared, take away x squared. Alright, so they'll cancel, because I'm taking away from itself. And I'm left with 2xh plus h squared. What can I do to simplify that? Factorise. Equals the limit as h approaches 0 of h outside of 2x plus h all over h. What can I do now? I like Michaela's action. Very dramatic. Okay, so it equals the limit of, take the limit as h approaches 0 of 2x plus h. Now we can substitute in 0 for h, and that's what taking the limit is, and we'll look at that in about a couple of weeks in more detail. But we'll just understand the process and we'll understand the application when we do it in functions and graphs. So, equals 2x plus 0. So replace now h, now replace it for the value that it approaches, which equals 2x. That tells you the equation of the gradient of the tangent at any x value for the function. Go back to your parabola that we looked at on Monday. Everybody. Further. Remember the parabola? We had 4 tangents. We had to calculate the gradient of those 4 tangents. This Monday's work. Page 59. 9. Got the parabola on the bottom, 4 lines. We had to calculate the tangent of them all. What was the gradient of line A? 2. All right, what was the x value of the point A? The x value of the coordinate of A.
Oh, yeah.
1. So, x equals 1. F dash of x equals 2 times 1, which is? 2 times 1, which is? 2. And that's your gradient of the tangent, isn't it? What would the gradient of line be? 4. What is the x value of the point B? 2. 2 times the x value, 2, which is? 4. What about C? What is the gradient of line C?
0.
What is the x value of the point C? 0. 2 times 0?
0.
Wow. And D, what is the gradient?
-6.
What is the x value?
X value was -3.
-3. 2 times -3 is?
-6.
Isn't that cool? Oh, come on. I expected people just to be just amazed by
If
it.
Robin was here, and kind.
I blame Robin then.
Oh, that's so cool.
There we go.
But how does it happen? How does it happen?
Now I should actually turn the camera around and record it.
If you've actually got it all on that. Oh, we should tell him it's really important. He has to watch this lesson.
He won't. He's gonna come back and he's like, because like,
So, for the parabola y equals x squared, what is the gradient of the tangent at the point 5?
it looks so confusing. He's gonna be like,
So if I took the parabola, it would be 5, 25 would be the point on the parabola. What is
5? Is it 5? Or 1/5?
if I take the parabola,
Yeah.
okay, I'll take the x value 5, the y value is
25.
both. The y value is
Is it like
25. And if I were to draw the tangent to that point at x equals 5 on the parabola, what is the gradient of that tangent?
10? 5?
Hey?
5?
No?
Well,
Why was it 1?
Hey? No? What is this? What did I tell you this is? F dash of x is the equation of the gradient of the tangent at any point x on the turn. Speak up louder, I can't hear you.
3 times.
Yell it, stand up, throw something at me, get my attention. Okay, I was referring to the coordinate. I was referring to the coordinate there.
It was like 10 before you
10.
were asking.
Yes. So at the point x equals -4, what is the gradient of the tangent at that point? No. What is it?
X equals what was the question?
Yes?
Negative 8?
-8 is the gradient of the tangent. You said 10!
we said 8.
You said 10!
She said negative 8.
She said 10. I heard 10.
I think you might be watching that again, so.
So you're going to need to watch this video.
Yeah.
You're making yourself watch this.
I might have to watch a video today, yeah. Work on my listening skills.
Negative 8, no. I'm kind of like, negative 8, yes.
I'm sorry, Mina. I swear I should have heard 10 from you. Alright, B, f of x equals x squared plus 3x plus 2. What type of graph is that?
Parabola.
Parabola. Okay, so we'll get those next topic. So we want to find the equation of the gradient of the tangent, right? And that is what this formula is. So before we can substitute in the formula, we need x plus h.
What?
X plus H.
Yes. So I need to substitute. So if I was substituting in f of 3, it'll equal 3 squared plus 3 lots of 3 plus 2. Yeah?
Yeah.
Okay, so x plus h, we'll be doing x plus h. All squared plus 3 lots of x plus h plus 2.
All right, you know.
Tidy that up.
Okay.
X squared plus 2xh plus, we of course all know that. This is chapter 2x. Anything we can tidy up? Nope. Alright, so the equation of the gradient of the tangent is f dash of x. So we take the limit as h approaches 0 of f of x plus h, take away f of x over h. And yes, you need to know this formula. Until you take the limit, you need to keep writing this. Okay, we're not doing anything with the limit yet. So we replace f of x plus h with what we've just expanded there. X squared plus 2x h plus h squared plus 3x plus 3h plus 2.
Sorry, Mom.
And we still need to write take away f of x. So take away, now you need your brackets because there's more than one term for f of x of the original function. All over h. The idea is to simplify, factorise, cancel out the h on the bottom with what you factorise out the top, and it'll give you the equation that we need. Right, you might need an extra line of working, you might need to expand the negative.
Yeah, really simplifying all of
Alright, so after you tidied up, simplified, you should get that line.
Where you off to?
Okay, if you can't do that in one step, you will need to expand this and then simplify in your next line. Alright, but I've already taught you how to simplify and expand all that sort of stuff. Right, what do you notice about 3 terms on the numerator? All got h in it. So, the limit of h outside of 2x plus h plus 3 all over h. That's what you're aiming for. You'll be able to cancel it out so that you can then substitute in 0. So it equals 2x plus 0 plus 3. So now after you've cancelled, we now substitute everywhere there's a h, we put in 0. 2x plus 0 plus 3 simplifies to?
No, you're wrong.
Now I have witnesses.
What is it? What's the answer?
Alright. What does this tell you? What is this? The equation of the equation of the what?
No, what is it? The f dash x?
Yes, which is the equation of the gradient of the
We're so...
Of something. I
That's
forgot what we're doing.
that's a bad way of saying the first.
Of the parabola. You know?
equation of the gradient of the t
Tangent.
Turning point.
tangent.
Oh.
You didn't say that, did you? You didn't say tangent?
I definitely did.
Alright, so quick sketch.
Wild.
So in order to sketch the tangent, what was the original? X squared plus 3x plus 2.
You got one.
Can someone tell me the time?
It's 5 past.
Alright, last one.
That's good.
Now we'll do a quick sketch from this. X squared plus 3x plus 2. We need to factorise. So two numbers multiply to give 2. Same two numbers add to give 3. Alright, so x plus 2. X plus 1. So we're getting the y value setting that equal to 0. So x equals negative 2. X equals negative 1. Alright, that's your factorisations in chapter 3, which will be applied in chapter 5. So there's a quick step there. That means when y is 0, x is negative 2 and x is negative 1. And there's plus 2 there. Okay, so that's the quick spiel where the parabola is. We'll look at that in more detail next topic. So, for any x value I pick, because it's a function, it means all x values do exist. If I substitute that x value into the equation, 2x plus 3, that will give me the gradient of the tangent at that point. Alright, so let's pick a couple. So x equals 1. What is the gradient of the tangent at x equals 1?
Oh, okay. So,
5.
5. Alright, so at x equals 4. What is the gradient of the tangent at x equals 4?
Yeah.
Mm-hmm. What's halfway between negative 2 and negative 1?
Negative 1.4.
Alright, so what are we expecting the tangent to be? 0. Okay, so let's validate it. 2 times negative 1.5
3, negative 3.
plus 3.
No, he's freaking me out.
I was expecting a lot more amazed faces at what was happening today, but anyway.
Oh yeah, you need Robin for that.
Yep.
Nice faces. I'm just thinking about my party.
Thinking about my time.
Okay, so that's pretty much the lesson. We'll